on the computer. And sorry guys, when you just inform your group, just please put the name of the people on your group on a Google Classroom that I can know who is who. Now, okay, let's get started. Now, what we have done so far. Logarithmic. Yes.
Do we have to make it on a video or can it just be
Sorry, what?
Can we just do the question or that's like on the whiteboard?
You can do that, for example, on a software, for example, which I do. For example, a screencast-o-matic software. This is free. This is free. Then you can record it like that. But whatever you do, you have to show you anything recorded on the Google Classroom. Maybe one question, that's it. You can do more stuff, but this is the minimum, you know, in case if you want to participate. There is no obligation at all. Awesome, thank you. Okay, guys, please everyone listen. No words, please. I can hear some people are still talking. Guys, we're just gonna start. Okay, now, for very quickly, I'm just gonna review what we did so far. Then we just go into the logarithmic equations, which is gonna be the new topic for today. Okay, what we have done so far. If you remember, we said that, Nick and Ash, we said that the exponential functions, such as the one which I'm gonna define it right now, which I'm gonna introduce a base as a, then I'm gonna raise it to a power f of x. The power exponent is a function of the x itself, and that's the reason we say that exponential function. But you remember also, when we defined this, we had some restrictions imposed on it. The first one was that the base necessarily has to be a positive real number, and also base cannot be equal to 1. Then we saw that from a couple of sessions ago that we can just work with his twin brother of this representation, because we said that we have one single reality, and that single reality is going to be represented in two different formats, two twin brothers. The other format was this. We said that we can take the logarithm from both sides, and you say that the log of y with the base, which is going to be still the same thing, a, should give you what? Should give you f of x. These two things are essentially the same thing. The exponential representation and the logarithmic representation, they were both representing the same thing. And we solved so many problems of it. Oh, by the way, you notice that for both of them, we have a single base. For both of them, we impose the same restriction. However, we said that when we just work with the logarithmic function, we have to, for example, if I just go back to give a quick example of what we did before, we said that look at this one as an example. As an example, we solved a very simple equation. We said, imagine that we are asking to find this. We said, what is the log of, for example, let's say 100 with respect to, let's say, for example, the base of 10. A very simple equation that we solved. We said that, okay, what is going to be the value for it? On purpose, I give you this example because on the next slide, I'm just going to introduce you a new identity. And that's why we start by this very simple example. We say that, okay, we have an expression like that. the log of 100 with the base, which is 10. Hi, how are you, Kathleen? Awesome, thank you. We said that what is the log of 100 with the base 10? And still we see that the base satisfies these requirements that it is a positive real number and also this is not equal to 1. We said that we said that sometimes we don't like to just work with this brother. We don't like him. Let's go to see his twin brother to understand what is a representation. If you remember, we said that we have a counterclockwise strategy to represent it into an exponential format, because the logarithmic format sometimes is the ugliest form. It's not, I should say, the user-friendly. We say, okay, we do not like this brother. Let's move on to the other one. What is the other brother? We said that that's how we find it. We say start from the base. I'm going to write 10. I move counterclockwise. I go to this box, which I need to find it. Then it means that it has to equal to this number 100. Now, this logarithmic function and this exponential function, they are exactly the same thing. Two twin brothers exactly looking at each other, and they represent the same reality. Okay, now from here, it's going to be more obvious what did we mean. We said that 10 to what power it should go to give you 10? 2. Then as a result, we say that 10 to the power 2 becomes 100. Then as a result, we say that the same thing here, it has to be 2. Because this is square, the empty square, they are the same either in the logarithmic representation or exponential ones. Then as a result, log of 100 with the base 10 equals 2. Now, it was a review of what we did. We introduced 3 identities, which we are going to move on from this one today. We said that we have 3 identities, 1, 2, 3. I'm going to add 1 more to that, 4. Then we solve 2 problems today. Then we are going to be done. We said that the first case is that the log of fx, a product with another function with the base 1, you can decompose it into the log of 2 different functions. We are going to see these identities over and over again. The second identity that we discussed was decomposition of a ratio f of x with g of x with the same base a. You notice that you can decompose them into a subtraction of 2 functions. Still the same base. The third identity, which we have worked a lot on it, that was a very interesting one. We said that we have a function f of x, still with the same base a, but it has been raised to the power n. We notice that the exponent can change its place and become a coefficient. Then n goes back before, I should say, the operator of log. Then you have f of x with respect to the same base. Now, the fourth identity, which I'm going to introduce right now, it's somehow from the same thing that we had is this identity. We said that the log of, this one is a little bit new, it's the derivation of the third one. We said that the log of, for example, we have a with the base a, however, it is raised to the power n. Then we say, what is that going to be? We say that, okay, I can now just take a look at the end, which seems as a hat on the exponential function, use the third identity to introduce it as a coefficient instead of as an exponent. then I'm gonna get n times the log of a with respect to the same base a. Then it's going to be how much? Hi, how are you, Jackson? Good, thank you. Then it's going to be how much? What is the log of a with respect to the same base a? Who said 1? Let's see. Let's do this as a side note here. Look at this. I say, what is this? What is the value of this? Again, the same thing. The log function is ugly. We just want to represent it with respect to its exponential representation. Then what do? We do that. Okay, we just start from A. The counterclockwise direction moves towards this. A raised to a power, it gives us back the same A. What do I have to fill in that empty square? 1. Then as a result, we notice that it is something that, as a side note, that we can learn it, that the log of A with respect to the same base is going to be always 1. It's so easy to understand that. The log of A with respect to the same base, it can become 1 because we can represent it as an exponential transformation, and we see that it has to be necessarily 1. Then as a result, the log of A to the power n with respect to the same base becomes how much? N multiplies to 1 equals to n. And that's the new identity that we have it right now, and it's so easy to prove it based on all the things that we know. There is one more identity which is related to the change of the base. We're going to talk about it next session. Now we are just going to do one example. Any questions so far? All the things so far was a kind of a review of all the things that we have done since 2 sessions ago. Now, we are going to solve this one together based on the identity 1, 2, 3, and 4, which you learned just in the previous slide. We are just going to simplify this expression. It's going to be the index of 4, a raised to the power 2, b raised to the power minus 3 over 4, and also c, which is raised to the power 1 over 3. Now, and notice that also the base of my logarithm is missing. Look at this one here. There is no base. It means that what is the base? 10. If I do not write it here, it means that the base is taken as 10. We are getting lazy. We do not rewrite the base if this is 10. Chloe, maybe you were not that session. We said that if we have, for example, the logarithm of a function f of x, the base of it is 10. Because it happens many times in the math, we want to save time. You must not use too much energy. Then we do not write that base. We simply write the log of f of x. Then if you see that the base is missing, it means that it is 10. Good? Now, give it a minute try to see that if you can, Michelle, simplify this expression and rewrite it in a very squashed form, a very simple form, using the identities that we covered here. Identity number 1, identity number 2, identity number 3, and identity number 4. 4 is the easiest one. Okay, shall we do this together or you need more time? You need more time? Shall we do this together? Awesome. Okay, first of all, we just to start, what is the purpose? The purpose is that we are not going to solve anything. We have been given something. For example, somebody has given you a potato. You want to chop it into make French fries. And that's what we want to do. We want to simplify everything as much as possible. How to do this? The first point, the first starting point starts with this index that we have here. You remember that when we talked with respect to the rational exponents, we had one very important identity. I'm going to rewrite this. We have this identity. We said that if we have a base, which is a, it is raised to a power m of n. One of the ways that we were able to rewrite this expression was this. We write it as a, which m falls as a direct exponent. Look at this m. The numerator of the rational exponent falls as a direct exponent of the base. However, what happens with respect to the n? N just go as an index of this operator. And that was a very important identity we discussed. Then you say, okay, as an example, what is going to be this? For example, a to the power 1 over 4. We say, okay, what is the issue? The issue is that I have an exponent which is a rational number. It's so hard to work with the rational number as an exponent, but we have a solution for it. And what is the solution? Is that you write the base intact. The numerator of the rational exponent falls as a direct exponent of the base. However, we have to introduce the denominator as the index of this operator. Then, if that's the case, look at this one which we have here in front of the log. We have the square with the index, which is 4, and we see that whatever is inside this square bracket, everything can have just the exponent 1. Then if that's the case, I can rewrite this expression like this. Let me change to a different color. I can rewrite this expression like this. Say the log of, I get whatever is inside the operator. One of them is a to the power 2. One of them is b to the power minus 3 over 4. The other one is c to the power 1 over 3. I have 4, which I know that it goes as exponent altogether 1 over 4. Why? Because we introduced, not right now, a couple of sessions ago, this very useful identity. So far, that's the basic thing that we could have done to just remove this ugly looking operator, which comes with an index of 3, 4. Now it's much easier to work with it. Why? Because if I come back to this identity, which we have always an exponent n for the log function, then I can have it as the coefficient. What does it mean? It means that I can rewrite it in like that format. I write 1 over 4 times the log of a to the power 2, b to the power minus 3 over 4, c to the power 1 over 3. So far, so good, everyone? Yes, Caitlin? Now, we see that still we have a lot to go. we see that the function which comes inside, I should say, the log operator, it's a product of three terms. And it brings us back to identity number one. You have the function is in front of the log. You have the function in front of the log as a product of two different terms. Then you decompose that. I'm going to do the same thing here. What I'm going to do, I'm going to rewrite it like that. I say it becomes 1/4 log of a squared. Look, guys, everything here is multiplied. A squared is multiplied to this, and this is multiplied to this. Plus the log of b to the power -3/4 plus the log of, guys, please be quiet, over 3. You see? From this step to the next step, I use identity number one. Because in front of the log, I had a couple of terms that they were squashed together by multiplication. I decomposed them into separate log functions. And that is nothing, just using identity number one. In number one, we had two functions, but you can expand it to the product of more than two functions. Now, look at this one right now here. Exponents 1/2, exponents -3/4, exponent 1/3. The same thing. We have a log function which has an exponent. We can take that exponent as a coefficient. That's what we're going to do at this stage. It means that the thing which I'm going to do, I keep 1/4, which is there. I took 2 as an exponent to fall off as a coefficient. Then we have 2 log of a. Now, we have -3/4, which is going to fall off as an exponent, becomes plus -3/4. I write simply -3/4 of log of b. And the same thing, 1/3 as an exponent falls as 1/3 as the log of c. If you have some time, you can just add, multiply 1/4 into the whole expression, but no need to do that. We stop from here. Interesting, huh? Yes. Oh, yes, look at this, because it becomes plus -3/4 log of b plus -3/4 becomes -3/4. Oh, from here to here. Oh, look at this one. Identity number one. If you have log of two functions multiplied, they are decomposed into the sum. And that's the reason. Identity number 3. I have an exponent. The exponent falls as a coefficient. Yes, Nick? Awesome. Guys, because we are going to leave the class today 15 minutes earlier, we're going to skip the break. Now, the next example, I want you to do this one. As a next example, do this. Do the log of x to the power 3 over the log of y to the power 3, however, with the index of 4. Now, let's do this. Let's see what is the most simplified version of it. Squash it to see that if you can make it as simple as possible using the identities 1, 2, 3, 4. Guys, have you seen the number, Neper number, E, 2.71? Everyone has seen it? Yes? I'm gonna be a little bit creative now. Put the exponent as the E, not the exponent, the base as the E. If you forgot it, E, this is called Neper number, or the natural number. It's around 2.71. For some historical reason, it's stuff like 2.71. We just write it E, which is called the Neper number. And I put my base of the logarithm as E. It means the base is 2.71. Simple as that.
I know. Oh, that's where we went for that's like kind of downtown. Yeah. I want to go to the United States since 2015. We're going. Yeah, I'm dead serious. I know. I'm sure you're not. No, I'm you guys are good. I really want to see it. It'll bring me back to my experience. Yeah. So I need to.
Yes. Guys, I'm gonna solve it. Then I give you some time to form your groups. Then you send me in the 15 minutes that you have that I'm gonna leave early today. Then you form your groups and put that on the Google Classroom. Put the name of your group, the people who are in there. Okay. Now. Okay, guys. Now, look at this one. First of all, we look at this expression. We see that there is some kind of similarities. There is some kind of similarities between this, I should say, and identity number 2. Guys, what time the class ends? 9:40. Yes, 9:40. Okay. Now we see that there is a similarity between that expression and identity number 2, which we see that identity number 2, we have a log as an operator, but there are 2 functions that they're being divided. Now, what does it tell me? It means that when I come to look at this expression, I see something similar. I see a function which is expressed on the top, such as f of x, and there is another function which is expressed at the bottom. It means that simply you can come here and rewrite it as, let me write it in front of that. Write it like that. We write log of square root of x to the power 3 with the base e minus the log of square of y root of, I don't know why that happens, to the power 3 index of 4. And that's the first thing which we did so far. The basic thing is that we saw 2 expressions. They are divided. We decompose them into a subtraction. And please notice that in all of them, the exponent remains the same. Sorry, the base remains the same. Ah, what happened? Okay, the base always remains the same. Yes, of course. Now, the second thing, I'm just going to use the identity that I expressed it here. The rational exponent when the exponent is m over n. When I look at the first term, I see this, I should say, this operator, I can rewrite it like that. I write it log base e, but x is here, and I have 3 over 2. This represents this expression. Why? Because the index here is 2. That's why we do not write it.
Why is it 2?
Because that's the square root. Square root, we do not write 2 because it's assumed to be 2. Like the log, when the base is 10, we do not write the base. What is the next term? Is the log of the same thing, y, I have 3 to the power 4. 3 over 4. The same thing. Rational exponent. Now, I notice that I have these identities. I have these exponents. I can just use identity, this one, identity number 3, to turn them into the coefficients. And guys, please quiet. Russell and Pierce. Then it becomes 3 over 2 because I can just take this now as a coefficient of the log x with respect to the base e minus. The same thing happens with the other coefficients. 3 over 4, the log of y with the base e. And there we are. That's done. Now, I'm just going to introduce something to you. It's a kind of a notation. Next session that we meet, I'm just going to expand more on it. But just that's a symbol. Okay, so look what we have done here. We have the logarithm with the base, which is e. It is going to be one of the most frequent logarithmic functions that you're going to see for the rest of your life. Then as a result, in order to make it distinct, I'm just going to introduce this notation, Daniel. I'm going to say, this is a kind of Kelvin and Daniel, please. If I say, I have a log of a function which its base is e, I'm going to rewrite it just in this format. I'm going to write it as ln of f of x. This is just a matter of the symbol. We say that if the log has a base of a natural number, we do not write the log of f of x with the base e. We form it and express it as ln. Then ln means the log when the base is e. Then as a result, I just want to be a little bit creative at the end of my response. Instead of writing log of e, I'm going to write ln. Then it becomes 3 over 2. ln of x minus 3 over 4. Again, ln of y. ln is more artistic way to write it. Instead of writing log with the base e, I wrote it log ln. Now, I'm going to give you a quick exercise, which you are going to do this and bring it next session for me. And the exercise is going to be this. I call that as a homework. And the homework is going to be this. I'm gonna ask you, please, solve 5 to the power 2x plus 2 equals to 3 to the power 5x minus 1. It's just gonna be a homework, but don't panic if you cannot solve it, because I'm gonna solve it next session. We are gonna introduce a new technique to solve this equation. Just give it a thought. If you cannot solve it, that's totally fine. But we are gonna come back to it. That's right, 3 to the power 5 x minus 1. Okay, now. Yes.
Go back to the slide.
Sure. You mean this one?
Yeah.
Yes. Essentially, by doing that, you are done for today. And Angelique, any questions?
No.
No. Angelique, now we are just gonna finish the class, but the people who are in the class, they are just gonna stay behind to form their groups, and then just put the group's number on the Google Classroom. I'm just gonna put further instructions of what do they need to do on the Google Classroom. However, you please stay in touch with your friends here by email or the phone and join one of the groups that you prefer, okay?
Okay.
Okay. Awesome. Let me also